Chapter 2 is about environmental systems, and they start with a case study of a lake in California known as Mono Lake. It's a terminal lake, which means water flows in, but water doesn't flow out from it. And it wasn't in the early 30s, 40s really considered a very valuable asset or resource to humans because there weren't any fish in the lake. There were just fly larvae and brine shrimp, which are very tiny little organisms. And the reason that there were no fish in there is because it was very, very salty from the fact that the water was flowing in, depositing minerals, then the water would evaporate and left behind very salty water. So already in the early 1940s, Los Angeles was experiencing having more population than could be supported by the amount of water that was available to Los Angeles. So they decided to divert the water from the streams that fed into this particular lake and other lakes very much like it. So by the 1980s, about the depth of the water in these lakes dropped to about half. And when the water drops to about half, it also gets twice as salty. And in this case, it did start killing off, not only preventing having fish in there, but killing off the fly larvae and the brine shrimp. And the problem with that is that migrating birds depend on the brine shrimp in particular and the fly larvae, but they depend on these organisms on their migration route. And so very few were beginning to be able to survive the migration route for that reason. So the Audubon Society started a litigation to try to reverse course. And in 1994, that actually succeeded. And less water was drained from the rivers that fed into this lake, and it was allowed to start to refill. And it refilled to about 2/3 of its original capacity. And that was enough to allow the brine shrimp and the fly larvae to survive. So how was that accomplished? Well, it was mainly accomplished by using technologies that reduce the flow of water into households and businesses and restricting the amount of water that they could use. And it has been successful. So what are some of the lessons from the case study? So why don't you take a moment to think them over for yourself, and then I will comment on a few. So one of the lessons from this case study that pertains specifically to this chapter on environmental systems is that if you change one part of an environmental system, it can change many, many other parts because it is a system. They're interacting parts. So when you drain the water that would normally feed this lake, the saltiness changes and the organisms that live within that lake change, and then organisms such as birds that depend on those organisms no longer have that resource. A second lesson that you may have thought about when considering this is that sometimes humans look at a resource as to what it seems useful to them, as opposed to the environment as a system with many interacting parts that we could be affecting. A third lesson you might have considered is that we often don't see the consequences of what our actions might bring. We don't look ahead to figuring out what will happen if we do these things in the future. So that goes back to sustainability and being able to maintain resources in a way that they can be useful to future generations and available to future generations. And you may have come up with some additional ideas about lessons from this case study as well. So now we're going to get into the heart of the chapter and start to look at environmental systems. So here, here's a list of our key concepts. You can see that we're studying matter, energy, systems, and how it all relates to environmental science. And under each of these topics, matter, what is it? Energy, what is it? So we'll be defining them. And then with regard to matter, we'll look at the different forms that matter takes, qualities, how matter changes, and what laws govern matter. Similarly with energy, we'll look at what forms energy can take, quality, how energy can change, and the laws that govern energy. Next, we'll look at systems, and throughout we'll relate it to environmental science. So first, let's define system. It's a set of interacting parts, and by changing one component, other components within that system are also changed, such as in the case of the Mono Lake. So Earth is a single interconnected system. The air in China is, at some point in time, the air in the United States. At some point in time, the air in Europe. It's all interconnected. You might have heard about how the wildfires in California are actually affecting the sunsets and things like that in faraway states, things like, and not so faraway states, things like Colorado. It's changing their air quality. A few years ago, there were some fires in Canada, and the smoke was so intense and the airflow was such that it just came directly down to Cape Cod. And many citizens of Cape Cod were calling their fire departments saying they smell a fire, they don't know where it is, but it was actually just smoke from Canada. Not just the air, but water is also one interconnected system. And a molecule of water that may be in, let's say, South America will go around the globe, and over a period of about 100 years it will circulate around and eventually return to its original location. So to look at all of these, this giant interconnected system, we have to break it down into smaller components or scales. So you can look at a very small scale. In here, we're looking at a cod, a fish. To a physiologist, a cod is a system. It has different organ systems, like we have organ systems. We have a heart, we have lungs. Fish also have systems, and a physiologist might study that at a very small scale. A marine biologist, on the other hand, would look at a larger scale, where it might look at how that cod is interacting with, say, food sources such as herring, and look at the predator-prey relationship and the populations and so forth between two species that are part of a single system. The next scale up would be, say, an oceanographer that might study a system of ocean currents and their effects on the fish populations. And even up one more scale, we have a fisheries manager who might be looking at a larger system, an entire fishery, which contains many different fish populations and which is also affected by human activities and human laws, harvesting the fish, for example. On the next several slides, we'll look at basic units of matter. So it's a little bit of chemistry. We'll have a lot of vocabulary terms that you do need to learn. Those are written in green. Then we have some larger concepts as well that are in blue. So let's take a look at the next one. Okay, so first we're going to look at matter. Later we'll look at energy. Matter is, let's put up a definition. First of all environmental systems consist of matter. Matter is defined as that which has mass and occupies space. Kind of a circular definition. But it's stuff. It has to have mass and occupy space. Mass is the amount of matter an object contains, and it's not the same as weight. So, for example, picture a 125-pound human being on Earth. Okay? They step on a scale. And, gravity pulls their 125 pounds worth of mass toward the balance, the scale that they're stepping on. And because we have a consistent gravitational pull on Earth, that measure will be 125 pounds. If we took that same mass, that same person, and put them on a moon, the moon is much smaller than the Earth. It has much less gravitational pull, which is why the astronauts kind of bounce around out there. So because it has less pull, if you put that same person on a balance, on a scale, they would only weigh about 21 pounds. That's because they still have the same mass, they just have a different amount of weight, because weight is the amount of mass that is being pulled by a certain amount of gravity. Okay, so matter is made of atoms. Atoms are the smallest single unit of matter that we have, though within atoms there are other particles that are smaller. So the three major components of atoms are protons, neutrons, and electrons. Protons and neutrons are relatively large particles, and they are close together in what's known as a nucleus of an atom, and they make up the majority of its mass. And then in orbits around the nucleus are very tiny particles known as electrons that have very little mass and are circulating around. Easy way to remember protons, pro, like I am pro some issue. That means positive. Neutron is much like the word neutral. It means it does not have a charge, positive or negative. And electrons are like electricity. It's a flow of negative charges. Okay, so a couple more terms. An atomic number is the number of protons. So in this picture, we have carbon. And this happens to be what is known as carbon-12. But carbon usually has, let me back up. Carbon always has 6 protons in its nucleus. Its number of neutrons might vary, but it always has 6 protons in its nucleus. So if you have an atom that has 6 protons in its nucleus, it is carbon. And that's its atomic number, 6. Mass number is the number of protons plus the number of neutrons. We're not going to deal with that so much, but just so you know what those numbers mean on a periodic table. So we will deal with atoms and its 3 major components, and atomic number, which is the number of protons, and we'll also deal with isotopes. Isotopes are formed by having a different number of neutrons. So there's an atom known as carbon-14. It's still carbon because it has 6 protons in its nucleus, but it's 14 because it has 8 neutrons instead of 6. So 6 plus 8 makes 14, and it's therefore an isotope. Isotopes are important in science. Mainly we deal with them as radioactive isotopes, but occasionally some other isotopes are dealt with as well. All right, now we're moving on to the periodic table, so I would like to pause at this point and move on to screencast 2.